In this short video, what I'll do is that I will take you through this concept of a conditional expectation, something which we encountered both in FRM Part 1 and in FRM Part 2. To understand what a conditional expectation is, let's first recap this concept of an expected value or an expectation. Let's assume that we are working with a random variable, let's call it uppercase X, and we define its expected value to be e of x. In the case that my random variable x is a discrete random variable, a case in which I am given the values which x can take, and since it's discrete, I can tabulate or list these values. And alongside each value, let's assume I am also given the probability that x takes on this value xi. And these probabilities I'm, let's say, denoting by P1, P2, and so on. The expected value of x can then be computed very simply as a probability weighted average of all possible realizations of x. Simply speaking, it's like saying, take in the value of x which x can take, let's call it x1, the first value, multiply it with the chance or probability that x will take that value and sum it over all possible values which x can take. On the other hand, case 2, if x was a continuous random variable, then what is served to us is the PDF of x. So this PDF, if it was denoted by fx, then I can compute the expected value of x as very simply the integral which runs from xl, let that be the lowest possible value which x can take, right up till xh, which is the highest possible value it can take. The essence of the formula stays the same. It is basically x that times the probability that x lies in the vicinity of x. Now, in the continuous case, if you remember, I am not saying that this probability is the probability of x taking on the value x, lowercase x, because that value I know for a single point realization is 0 when my random variable is continuous. So here I'm saying let's still work with probability weighted averages, but I will work with a probability that x lies in the vicinity of this x, and this probability is given by fx dx. Okay. Now this was very quick recap of expected value for the case of a discrete variable and the case of a continuous variable. Now, before we move ahead, let's quickly understand the context in which conditional expectation is applied. We encountered two cases. There was a case which we encountered in chapters on regression. This was a case of computing, let's say, the expected value of y, which was my dependent variable, given I tell you what is the value which the independent variable has taken. Okay, this was a conditional expectation. Similarly, in chapters which were to do with market risk, and this was both in part 1 and part 2, we encountered this concept of an expected shortfall. Verbally speaking, this was a risk measure which captured the probability weighted average loss conditional on this event that the loss exceeds the VAR. Okay. Now let's come to the definition of a conditional expectation. Let's assume that I am still working with this random variable x, which I began this discussion with, and now I have one more random variable, let's call it random variable s, which I refer to as a conditioning variable. Okay. Now, based on some information about this conditioning variable s, I am, let's say, asked to compute the expected value of x. How will I write it? I will write it as the expected value of x given s, let's say, has assumed a certain value lowercase s. This conditioning variable, its information can be given in other ways also. Information such as s takes on a value which is higher than lowercase s, s takes on a value which is lower than lowercase s, and so on. There can be any event which we have, let's say, designed with this guy in the picture, the conditioning variable. Okay. Now let's come to the formula. This is how I'm saying I would write down a conditional expectation. Now, how would you compute it? To compute this conditional expectation, it's actually very simple. All we have to do is we have to go back to the formulas which we had for the case of a simple expectation and change the weighting scheme. Remember, the weighting was probability weighted. So what I'll do here is that I will switch from an unconditional probability in the case of this simple expectation to a conditional probability in the case of this conditional expectation. In the discrete case, very simply, it then boils down to it's the probability weighted average of all realizations of this random variable x, but the probability now is a conditional probability. It's the probability that x takes on a value xi given that s has taken on a value lowercase s, for example. Okay. In the case of continuous, it's again an integration, but I would replace this PDF, which is like a marginal density, or you can say it's like an unconditional density, with a conditional density. I would define that conditional density as the joint density of x and s, that divided by the marginal density of my random conditioning variable s. Okay. So in a sense, switching over from simple expectation to conditional expectation just amounted to switching the probability from unconditional to conditional. The essence of the formula stayed the same. Okay. Let's now do this. Let's apply this concept of a conditional expectation to a very quick example. Let's assume that I have tabulated the data of a given locality. This data is pertaining to n, the number of members in any given family in that locality, and x, the number of cars which this family possesses. Okay. So if I tabulate this data and let's say it looks something like this, then what I can do is that I can sum this data in this part of this matrix along two dimensions. If I sum it along this dimension, that means I am summing it up across various values of n. N is represented in this direction, keeping the value of x the same, which is equal to 0. And the number, let's say for x equal to 0, I get it as 23. Okay. Similarly, for x equal to 1, I get 89. For x equal to 2, I get 34. The total number of families in the locality is 146. So this column, it will help me arrive at the probability distribution of my random variable x. Similarly, this row, which I fill it up with, let's say, the sum of all these numbers in this matrix in this dimension or this direction, then this row will give me the probability distribution of n. Okay. So based on this data, suppose I were to ask you to compute the expected value of the number of cars in any given family, given I am telling you to only restrict yourselves to, let's say, family which contains 3 members. Okay, and that's why I have shaded this column. So if you were to apply our definition of a conditional expectation for the discrete case, what would this amount to? This will amount to a probability weighted average of the number of cars. Let's say it can take on a value xi, where I goes from 1, 2, 3, and xi is 0, 1, or 2. This times the probability of x taking on this value, conditional upon this fact that the number of members in this family is 3. Okay, that means I would write it as probability x equal to xi given that n is equal to 3. To work this number out, very simply what I can do is it will be 0 times the probability, the conditional probability of x taking on a value 0. That will simply be, it will be 4 that divided by 39. Okay, I'm restricting myself to this subspace. Okay, so it will be 4 by 39. This plus 1 times 24 by 39 plus 2 times 11 by 39. Okay, and you can check that this number comes to 1.179. Okay, so this was a very quick application of a conditional expectation to a very simple discrete case. Now let's do this. for the applications that we will encounter in FRM Part 1 and Part 2, let's devise an alternative route of computing a conditional expectation. The route which we have right now was to compute it using the same way as we do for a simple expectation, but just switching the probability from unconditional to conditional. In this alternative route, what we'll do is that we will compute this conditional expectation as a three-step procedure. In the first step, what I'll do is that I will transform the random variable whose expectation is desired. That's my first step. My second step is that I will compute an unconditional expectation. Okay, I will not compute an expectation which is using conditional probabilities. And number 3, I will divide the result which I get into with the probability of this conditioning variable satisfying the condition on this variable that was imposed on it. Okay, so this is my three-step procedure. Let me first tell you what this transformation is all about, and then we will apply this procedure back to our family members and car number example. Okay, so what is this transformation? Let's assume that it's X whose expectation I desire, and this expectation is conditional on some event around this random variable S. I have not specified the event here. I've just written it as S. Okay, it can be anything. S equal to S, greater than S, less than S, whatever. Okay, so if I am served this information that this event related to my conditioning variable S has happened, then that information basically polarizes or divides X into two camps. Okay, there is one camp of those values of X which correspond to that event which happened, the event related to S, and there is a camp of values of X which does not correspond to S having happened. Okay, so in moving forward, what we want to do is we want to only focus on or retain those values of X which correspond to S having happened, and chuck out those values of X which do not correspond to S having happened, that conditioning event, that event around this conditioning variable S having happened. Okay, so this verbal task which I mentioned, the task of retaining and chucking out, let me represent it mathematically as an indicator variable I. Okay, so if there is a value of X which corresponds to S having happened, for that I will multiply the original value of X with a 1, which means I will retain that value. That value is of use to me. If that value of X does not correspond to S and the event around S, I will multiply that value of X with a 0 because I want to chuck it out. That value of X will not be contributing to my expectation. Okay, and this multiplying with a 1 or a 0, I am saying, is captured by this guy I, which can only take two possible values, 1 or 0. Okay, that's what I call transformation. Now let's apply this transformation to see what it meant. Okay, now take a look at this table. In this table, I wanted to use it to compute the expected value of X under this event N is equal to 3. Okay, this is like conditional upon or given that N is equal to 3. So start from this guy. So for these families which have one member in them, these families do not correspond to my conditioning event. Therefore, these families, I will take the X's of these families. Okay, 9 families had a 0x, 11 families had a 1x, and 1 family had a 2x. And for all these families, I'll multiply their X's with a 0. That means I'm saying, let me assume that all these 21 families have 0 cars. That's what I have done here. Okay, I have moved the 11 to this cell and I have moved this 1 also to this cell. All 21 therefore have 0 cars. Okay, the total stays the same. It's 21. Similarly, these guys get moved over to this cell. Okay, they also are assumed now to have 0 cars. These guys also move over and therefore you have 36 guys having assumed to have 0 cars, and you have 0 guys assumed to have 1 car and 0 guys assumed to have 2 cars. In total, the number of families with 2 members is still 36, what we had before. Okay. Now this column corresponds to my event, the event which is, let's say, given to have happened. So these x's, the x's for these families, I multiply with 1. Okay, so these x's stay the same. 4 families still will have 0 cars, 24 families still will have 1 car, and 11 families still will have 2 cars. The total still is 39. Same transformation here. These guys, the 48 guys, move to this cell, and I have a total of 50 in this row, and the total stays as 50. That was my transformation. Number 2, let's compute an unconditional expectation of my transformed variable. And this is like numbers corresponding to my transformed variable. Okay, so how will I compute this unconditional expectation? It will be 0 this times this guy, the sum of these transformed numbers. So it will be 111 upon 146 plus 1 times 28 upon 146 plus 2 times 11 upon 146. Okay. Third step, divide this number which you've arrived at with the probability of n is equal to 3. Okay. And that probability is 39 upon 146. You can check that this number also comes to 1.179. Okay. Now comes the time to apply this 3-step procedure to our financial risk management application, and that is expected shortfall. Let me write down the formula first. So this expected shortfall is a conditional expectation. It's the expectation of your losses conditional upon or given this fact that your losses exceed the VAR. Okay. I'm assuming here that my losses are a continuous random variable. This is how its distribution looks like. On this distribution, let's say I have plotted where the VAR resides. This VAR helps me cut off this distribution into 2 parts. There is a body whose probability mass is C, and there is a tail whose total probability mass is alpha. Okay, the level of significance. C is level of confidence. Now, step 1, transform this loss variable. In this case, note that my conditioning variable S is the same as X. Okay, these needn't always be different. So my conditioning variable is also loss, and my variable whose expectation is to be calculated is also loss. So all losses which do not correspond to my condition are assigned a value 0, and these are losses to the left of the VAR. Okay, so all these losses get assigned a value 0. The probability of you getting this transformed value of the loss of 0 is the entire area in the body, which I have told you is the C. Okay, and therefore I put a probability mass of C on this loss of 0. And then the losses which do satisfy my condition, that means losses which lie to the right of the VAR, they will retain the same continuous distribution, this PDF which we denoted, let's say, by Fx. Okay, what has happened? In transforming this variable, which was a continuous random variable, from the original values to a transformed value, we have moved from a continuous distribution to some kind of a mixed distribution. It's a discrete plus a continuous distribution. Okay, this was my step 1. Step 2, let's compute the expected value of this new transformed variable, and let's compute it in an unconditional sense. So the expected value of this new guy will be 0 times its probability, which is C, plus the same way as we do it for any continuous variable, integrated between its lowest bound to its uppermost bound, and it's an integration of x times the probability that your loss lies in the vicinity of x. Okay, and therefore this is what you get. Third step, divide it with the probability of your condition happening, and we know this probability is equal to level of significance, and that's what we have in the denominator. Okay, take a look at the formula which we have now. This formula was presented to us as the formula for expected shortfall, and what we've done now, through this reasoning that we have put in place for a conditional expectation, we've actually proved this formula. Okay, we've arrived at a very intuitive kind of a proof which can help us remember this formula really well. Why is the expected shortfall equal to this? Okay, So this was a very quick and short video which explains to us this concept of a conditional expectation and how this expectation is applied to the context of financial risk management.